Last episode, you exported a trained model to ONNX and watched it run outside Python, identical to the digit it ID'd. So now it runs anywhere, but runs was never the goal. The goal is runs fast and small enough that the pager stays quiet. Today, we make the same model lighter without breaking it. Here's the trick. Nobody tells you up front. Most of a model's size is just the weights stored as 32-bit floating point numbers. That's 4 bytes for every single parameter, and a lot of that precision is wasted. The network never needed 16 significant digits to tell a 7 from a 1. Quantization is the move where you store those weights as 8-bit integers instead. 1/4 the bytes per weight, same shape of answer. Dynamic is the flavor that costs you nothing to set up. There's another kind, static quantization, that needs a calibration pass over real data before it'll commit. Useful, but it's a whole extra step. Dynamic quantization skips that. It keeps the weights as int8 on disk and figures out the scaling for activations on the fly while the model runs. One function call, no calibration set, no retraining. And here's the catch you have to respect. Quantization is lossy. You are literally throwing away precision, so the outputs can drift down in the low decimals. The real question isn't whether the numbers are bit identical, they usually aren't. It's whether that drift is ever big enough to flip a prediction and actually cost you accuracy. For a well-behaved model measured honestly, the answer is a fraction of a percent, and sometimes it's flat zero. We measure that number, we don't assume it. So the whole episode is 3 honest measurements stacked next to each other. How much smaller did the file get? That's a number in megabytes. How much faster is one prediction? That's a number in milliseconds averaged over a real loop. And how much accuracy did we lose? Also a number. No vibes, 3 deltas. The program trains a tiny digit classifier, exports it to ONNX, quantizes it with one call, then puts both versions on the same scale and compares them. It's seeded, so the numbers reproduce. We measure size of disk, latency with a timed loop, and accuracy on the same test set for both. This line is the entire optimization. Quantized dynamic FP32 path, int8 path, weight type, quant type, quint8. You hand it the float model you already exported, a path for the new one, and you tell it int8 weights. That's it. That's the whole make it smaller step. Everything after this line is just us proving it worked. Then we measure size the only way that's honest. os.path.getSize on each file, straight off disk, converted to megabytes. Not an estimate, not a parameter count times 4. The actual bytes the deploy server will have to load. We do it for both files so the ratio is real. For speed, we build one inference session per model and run the same input through a perf counter loop. 50 timed runs after a warm-up, because the very first call always lies. We average the loop, not the first shot, and we keep the input identical across both, so the only thing changing is the model. Run it. The float model lands around 2.5 megabytes. The int8 version comes in near 6/10 of a megabyte, close to a forward shrink. Latency drops from about 1/10 of a millisecond to roughly half of that. Call it twice as fast per prediction. And accuracy, the whole reason we're nervous, doesn't move at all. The same 98.5%, 0 points lost, smaller, faster, free, ship it. The hero card on screen plots exactly those 3 bars: size, latency, accuracy, FP32 against int8. Every height on that chart is a number you just read in the terminal. The near 4x size drop, the latency cut roughly in half, and the 2 accuracy bars sitting dead level. Figure equals terminal, no rounding tricks. Quantization is the cheapest speedup in production. One function call buys you 1/4 the size, and faster inference for a rounding error of accuracy. Next episode, we go bigger, vLLM, and how you serve a real language model fast enough for actual users.